The drawbridge here operates by a tensioned rope that can pull on the end of the bridge, causing it to rotate around the hinge at the left. When a real drawbridge is in the fully down position, it would probably rest on the ground at the end on the right. However, that would very much complicate our physics here, so we're going to pretend that the bridge is supported only by the hinge at left and the tensioned rope at its right end. This means as we move the horse and cart further and further right, the tension in the rope will have to be higher and higher to support the system against collapse. We can adjust the angle of the rope, the position of the horse and cart, the mass of the horse-cart system, and the length of the bridge. In order to see the physics of what's happening here, we need to show the forces acting on the bridge. When we flip the switch, we have access to the tension in the cable, shown in orange, the weight of the bridge, shown in red, and the weight of the cart, shown in yellow. All of these forces are expressed in newtons. Since the tension cable is at an angle, its two components, horizontal and vertical, are also shown. You might notice that the forces don't all add up. For instance, the vertical forces don't balance. There's a greater downward force than upward in the situation shown. Well, we can also show the forces acting on the hinge or pivot of the bridge at left. An upward and rightward force is what brings the entire bridge into force balance or equilibrium. The system is in force equilibrium, meaning that it won't accelerate horizontally or vertically. But it is also in torque equilibrium, meaning that it won't begin to accelerate in a rotational sense about the hinge. The cable pulls on the bridge, attempting to rotate it counterclockwise. The weight of the bridge and the horse and cart also pulls on the bridge. These attempt to rotate it clockwise. The clockwise and counterclockwise torques balance one another, and we're in rotational equilibrium. The graphs at top left and top right show the magnitudes of the clockwise and counterclockwise torques. On the vertical axis is the total weight of the bridge, horse, and cart. This is the vertical axis of the left-hand graph, plotted against the center of mass position. This is the mass averaged position of the bridge and cart system. The total clockwise torque would correspond to the area of this graph. The graph at right shows the magnitude of the counterclockwise torque due to the cable. Only the vertical component of the cable's tension matters to the torque here. Any horizontal component wouldn't rotate the bridge. This is plotted against the distance from the hinge to where the cable attaches to the bridge. When the bridge is in rotational equilibrium, the two areas represented on these two graphs are equal to one another. As you can see, if you lower the angle of the tensioned cable, the overall tension in the cable increases. In order to maintain torque balance, an increased tension force is required so that the vertical component of this force remains sufficiently high to generate a counterclockwise torque. Eventually, under the right circumstances, you can cause the cable to exceed its breaking tension and snap. Play around and see what happens.